Hi everyone, let's consider the graph of y equals f of x, which is 4x cubed minus 5x squared minus 7x plus 2. Now, two of these terms are immediately informative. The positive 2 tells us what? It tells us that the y-intercept for this graph will be at the point 0, 2. Because when you plug in x equals 0, these go bye-bye, and you're left with a constant term 2. But more importantly, the leading or dominant term, 4x cubed, tells us a lot. This tells us what the graph basically looks like in the long run if we zoom out. Then we can figure out the long run limits for this function. That's why I call this the zoom out dominance property. The leading term basically tells us what's going on. So how do we graph y equals 4x cubed? Because the graph of y equals 4x cubed will exhibit basically the same long-term, long-run behaviors as this over here. How do you graph y equals 4x cubed? It's going to be a rising snake. As x approaches infinity, as we look to the right, the graph goes up, up, up towards infinity. Y approaches infinity. As x approaches negative infinity, as we look to the left, the graph goes down, down, down. The y-coordinates or function values approach negative infinity. And the same is true for the graph we care about. Notice that the y-intercept is at 0, 2. That's what that constant term tells us. But the leading term, 4x cubed, which is the same as this, it tells us that both of these graphs will have the same long-run behavior for all practical purposes. It might be more helpful if we have unequal scales. Let's make the x-axis more like -5 to +5. And the y-axis is going from like -40 to 40. Okay, this might be a bit more informative. You can see that in the long run, right? Again, if you look at the red graph and the blue graph, the red graph and the blue graph, they both go up, up, up as x approaches infinity, and they both go down, down, down as x approaches negative infinity. They share the same long-run behaviors. Y equals x cubed is in blue here, and the graph we care about is in black. The graphs look similar in the long run. So here are the long run limits for both the 4x cubed function and also the function we care about. The limit as x approaches infinity, as we look off to the right, the y-coordinates approach infinity for both graphs. Likewise, as x approaches negative infinity, the y-coordinates, the function values, approach negative infinity. As x approaches negative infinity, the y-coordinates, the function values, approach negative infinity for both 4x cubed and the function we care about. The zoom out dominance property, that's my term. The leading term of a polynomial, f of x, increasingly dominates the other terms and increasingly determines the shape of the graph in the long run as x approaches infinity or as x approaches negative infinity. So if x is close to 0, then the blue graph exhibits some lumpiness, and that's determined by these two terms in the middle. The constant term just leads to a vertical shift, but there's more of a struggle here because of these two terms in the middle, and we get some lumpiness. We get a local max point up here, and we get a local min point down here because of these two middle terms. So if x is close to 0, basically, then these lower order terms can matter. But as x moves far away from 0, as x approaches plus or minus the millions, billions, trillions, the leading term is the term that really, really matters in the long run. And these lower order terms really don't matter at all. They barely matter at all. So if x is close to 0, the lower order degree terms can put up a fight for part of the graph, and we can get some local or relative maximum and minimum points, turning points. We do get turning points up here and down here. but in the long run, the leading term dominates. By the way, in calculus, you'll locate the turning points. By the way, one side note, if you have a special case like this, where you have, say, a fourth degree polynomial that can be factored like that, then it might be better looked at as a translation problem. For example, y equals x to the fourth looks like that. Y equals x plus 1 all to the fourth basically exhibits the same behavior in the long run because it just corresponds to a horizontal translation. Okay, next up, let's talk more about turning points and the possible numbers of turning points for polynomials of various degrees.